Good morning. My name is Mehnert. My name is Andreas. We're going to talk about security, IP networking, and the design of it, or rather with the subtitle Wireshark without the remote exploits. And we'll start out with a motivation of what we do and why we do it. So we noticed that a lot of software, especially security critical software, is itself vulnerable large number of times, and the existing processes don't seem to help. And so we looked at the major root causes of vulnerabilities and what we can do against that. And if you look at the CVE, Common Vulnerabilities and Exposures database, you can roughly classify the bugs you see by the type. So the blue is OS interface flaws, the light blue is logic flaws, the big green is data reference failures, so we all know it's buffer overflows. Yellow one is interface failures, and the red one is input-output errors. In more hacker-like terms, this is cross-site scripting and SQL injection, stuff like that. We see a certain trend here. People learned about the existence of buffer overflows and they started doing something against it, but it still doesn't help. It still makes up a third of all security vulnerabilities reported up to this day. We have a major issue with I/O errors and input sanitation as well, and OS interface flaws. That's for instance stuff like parsing null byte. If you have a Java program that passes a null byte in a string and then you pass it to the operating system and the name for the file OS sees is a different variable from Java, stuff like that. Okay, for these problems, well, of course, you can always say the programmers are lazy and they need to be more careful with their source code, blah, blah, blah. But reality shows that programmers do make mistakes, and that it's better to try to attack those vulnerabilities at the root. So trying to eliminate the pattern that causes the bug. And there are a number of workarounds applied to buffer overflows. That's like randomized address space, stack canaries, etc., etc. So instead of trying to prevent the buffer overflow, it tries to prevent the bug from being exploitable. And of course, this helps only to a certain point, and we've seen lots of talks on this Congress in the past years that describe how to work around those workarounds. And the real solution to buffer overflows is very simple. Do bounds checking on your buffers. Same problem for integer overflows, and if your language doesn't support checking for integer overflow, you have a problem, and the solution to integer overflows is either use big nums or for an exceptional overflow, and suddenly the problem is gone, another vulnerability is gone. And the third big source of exploitable vulnerabilities these days is premature memory use. Somebody calls free, somebody else accesses the pointer later on. Or some piece of memory is free twice. And this is often exploitable too. Other examples, number of examples of I/O errors are what I already named: SQL injection, cross-site scripting, etc., etc. This is usually curable by a better API design. So while the problems we've seen before, like buffer overflows, integer overflows, you need to have a language that provides bounds checking for you or integer overflow detection for you. So you need to choose that. And here you have to be careful in the API design to design your API in the language right. So look at PHP for instance. It doesn't have any buffer overflow problems, but it gets a lot of APIs wrong. And this leads to typical problems like that. Another quite common problem are format string exploits. And again, we see that the problem is that in some languages you can read more variable arguments from the stack than the caller put onto it, with disastrous results. And finally, race conditions. Then OS interface flaws. directly traversal illegal file access. And again, that's an issue of designing an API right. So in conclusion, we've seen that some of the problems that lead to vulnerabilities are addressable using mechanisms that are provided by some languages and are not provided by some other languages, like bounce checking and buffer overflows. And that another class of bugs is preventable by trying to design the APIs right. And since we were interested in writing network analysis software, because we've seen tools like Ethereal, or this is called Wireshark, has 112 CVE entries had in the last 5 or 6 years. It literally has hundreds of vulnerabilities. As a security researcher, you cannot open just some random feature file because it might be exploited by an ODE in Wireshark. And that's a situation we didn't want to have. So we wanted to be able to write lots of networking code, and we wanted to be secure. So we had to choose another language than C. Of course, we also had to choose another language than, say, PHP. And the language we've been using in the end is a programming language called DIL, which is kind of like Lisp, but without the brackets. So that's the high-level view. So it gives a lot of powerful features. It looks a little bit like Pascal. It's got, it's an object-oriented language. It's a dynamically typed language. It provides automatic memory management, so no problem with freeze. It provides bounce checks, so no problems with buffer overflows. It provides integer overflow checks. And additionally, it gives us the power to write APIs in a fashion that is much more secure. So if we are able to design a higher level security features into our software. And that's by powerful abstractions that are provided, like higher order functions and dynamic types. So very important here is that the difference between weak and strong typing and dynamic and static typing. For instance, C is statically but weakly typed. You can always cast a pointer to something else. ML is a language that's statically and strongly typed. You can cast just a pointer anyhow. And I think fourth would be called weakly typed language, maybe. But what we have is dynamically but strongly typed. So basically it feels like a scripting language. It gives you the ease of use like you would expect from Python or Ruby or Go or languages in the ballpark. Okay, so we have a language and then started designing our network analysis framework on top of it.
Okay, we have the problem that we want to have an architecture for a secure network state. So we divided the problem into three sub-problems. The first is packetizer, which is a domain-specific language to parse and assemble protocol definitions. Then we have a flow graph library, which is inspired by calling the modular router framework from UC Berkeley. You can specify the flow, how your packet should flow from the Ethernet interface to your IP stack and so on. Then we developed a layering mechanism to stack protocols like how to speak TCP over IP and so on. The underlying structure we used is a stretchy byte vector subsequence. On the top you see a full byte vector with some bits, and you can subsequence it bitwise. So you can say, let us start at byte 3 and let us end at bit 5 of byte 20 or something like that. So you get access, you get bit access if you want to have that. And the structure is always the same vector, but you you have a start and end offset also in the structure, so you are not able to access other data, but the subsequence you really got.
Yeah, the two important points here, I think, are first, it's the zero copy. So we get in a byte vector, which is our network packet or something we want to disassemble. And in the parsing process, we determine that subsequence is the header, and that subsequence is the payload. To pass on that to the next parsing module, we pass around subsequences, which capture the original vector and it bounce into that vector. So you always pass around one object. You cannot forget to pass around the bounds for that object. And of course, access is checked. So if there is an error in the parsing process, you'll notice because you will access your subsequence on the bounds.
Okay, that's the underlying structure. So we thought about the problem of protocol definitions. And we came up with a solution which that we have some sort of frames which are like IPv4 address, MAC address, strings, integers maybe somehow of different size and of different encoding and so on. Then we also have variably size data structures like payload or data. Yeah, and we came up with two properties we have on those frames. The first is the size property. So IPv4 address, MAC address, and those integers are fixed size, and strings and payloads and data are zero terminated, or you have a string where the count field is prefixed. So you first get a count field, so let us say 20, and then you get 20 bytes of the string. Yeah, well, those frames are variable size, so it's not clear at compile time how long they will be, but it's clear at runtime, of course.
Okay, maybe for understanding a bit here, we basically looked at existing definitions of packet formats. We call every collection of bytes that have some meaningful structure a frame, and try to understand how real-world frames look like, to find an abstract description language for the layout of those frames, to come up with generic algorithms for parsing and assembling those frames. And yeah, so that's the fixed size versus variable size is one of the properties we found there from examples. So there is some prior art that also tries to use generators for parsers and assemblers. ASM1 is something that probably rings a bell to many people. And it tries to achieve the same, but with a big difference that it's only applicable to stuff defined in ASM1. You cannot just take an arbitrary RFC like TCP and describe it using ASM1 and have it work. So we had to do something different. And it turned out that the reality of protocols is very, very complex.
Yeah, the other property we came up with translation. Sometimes you have fields in a frame, or you have fields like an IP address or MAC address which are untranslated. So you have a type or a class for those frames, and you don't translate it to a higher level. But on the other hand, you have something like strings, zero terminated strings, and so on. And you want to have access via built-in DOM type string to that field, to that frame. The same as integers. You want to have at high level in integer, a normal integer, and not a specified subclass or whatever. So we call those frames translated, which have a high level type, or which have a DOM type, a built-in DOM type as high level type.
Yeah, the translation is also where we care about stuff like endianness. So you don't have, while writing a program, you don't have to think about what endianness you're on, or think about calling the right translation function. It's just built in. When you declare a frame, which is the data in an example, you say, this is a little endian 32-bit unsigned whose complement integer, and it will know how to translate that into a number in your high-level representation, regardless of platform.
Okay, that's our, it's our class hierarchy of a frame. So a frame is a superclass of all that frames we see in a frame. So basically we have leaf frames which don't have any internal structure. So leaf frames are is stuff like an IP address or MAC address and so on. Then we also have, as I already told, fixed size, variable size, and translated and untranslated frames. Yeah. Then when we look at leaf frames, we have different kinds of leaf frames. We have fixed size untranslated leaf frames, variable size untranslated leaf frame, and fixed size translated leaf frames. That's basically because we want to come up with a generic parsing and assembly algorithm for stuff like IPv4 and MAC addresses. So we can specify parsing and assembly on fixed size bytevector frames because it's always the same. The only difference is that IP address is 4 byte and MAC address is 6 byte. That's why we chose this class hierarchy.
Okay, we introduced leaf frames, which are frames of no further structure, like MAC address. And the opposite are container frames, which consist of a number of fields. And fields are characterized by having a name and being in itself a frame again. So it's if you know design patterns, it's basically the composite pattern. The container frame consists of a number of either leaf frames or container frames with a name. And we provide, when you define your frame, there's code generated for accessing the fields of the frame. And you see here the notation in the declaration we use for specifying the fields of that frame. So it has a name, every field has a name, every name has a type, which again is a frame, and a start length and sometimes an end address. That's because there are many ways how protocols define where a certain field starts or ends. Like in a simple example, like that Ethernet header, you know that at start address 0 you have the destination address, at start address 8 you have the, at 6 you have the source MAC address, etc., etc. So it's statically known. But you also have dynamic cases like the start of a payload in an IP packet, or you might have some zero terminated string, and you get to that in the next example. One more interesting aspect here, you see in the end of your Ethernet frame you have a payload, and that payload can be a number of different frame types. It could be an IP frame, or it could be an ARP frame. What exactly it is depends on a value of another field frame, and for that we are able to write expressions. So in the type declaration of a field, we can write directly the type, or we can write an expression that computes the type based on some other information. So we are very flexible here to express how protocols stack into each other.
Yeah, the next example is IPv4. It's a bit more difficult because IPv4 has some special properties. So we implemented stuff like default values. The version field of an IPv4 frame is always 4, or should be 4. So when you want to generate a IPv4 packet at high level, you don't want to specify the version field, because it defaults to 4. But you want to be able to specify that the version field should be some other value. So we have support for default values, but as a developer you can also specify your own values if you want to. We also have as you see in the header length field, or the arrow pointing there, we have fixer functions. So we can write a fixer function for the header length, which is by default the size of the IP options plus the header divided by 4. Which is
so this gets into play when you try to assemble a frame. So basically what we end up with, if you write down the frame definition, we've seen parts of it, is that you get a high-level representation object for the frame. And the basic operations are parsing a frame, so you take your byte vector sequence and you get a high-level representation, or you can do the other way around. You want to send a packet, so you have some syntax to create the packet, and then it needs to be assembled together into a byte vector. That's where the fixer functions come into play. They are called to compute the value of a field, and this is what we do here. So if you create a packet, you don't have to calculate your header length yourself. It just gets automatically calculated for you when you call the assembly function.
Yeah, we also have support for dynamic start and end offsets. So during parsing, you may want to be able to access only the payload of an IPv4 packet, but it's not that easy because the payload depends on how long the options and padding field is. So we can annotate to the payload functions or build expressions where we can specify where they start, where they end, how long they are, and so on.
Okay, so if you remember in the frame before, we had for static start and static end or static length expressions. So we have to specify 2 out of them. And here in that field, we have a dynamic expression, which is an actual Dylan expression that gets evaluated, and which then automatically gets the header length and translated into primary representation for computing the actual offset of the payload. All this happens cached and dynamically, by the way. So if you say, I have that frame here, or I have that IP frame here, please give me a high-level representation. Basically what you get is just a handle, a type handle to your byte vector. And only if you really start accessing something in the packet, like a payload, it goes and tries to compute the start address and the end address, and calls the right parser to extract the information for you. And it's during that process that it notices that it actually needs to pass the header length. So it again goes, passes the header length, gets the value. So it tries to keep the effort for getting the information you need as small as possible. So again, with a benefit in performance.
Yeah, the next problem we encountered was IP options. IP options are quite, they are typed internally. So they first have a flag field, then a class, and then a number. Altogether it's a byte, and this byte specifies what comes next. So we implemented that as a frame inheritance. So all IP option frames inherit from the IP option header. Yeah, we have IP options like router alert, which specify that is talked at we are type 20. So the IP option header must be 20 to be in router alert frame, and then next is a length field and a value. The other thing is an end of IP options. It's 0, so the IP option header is all zeros. Yeah, and there are no other fields in an end of IP option frame.
So, yeah, we mentioned repeated fields here. That's something you'll encounter, that you have a variable number of objects of the same type. And the real world, again, is complex. There are different ways in which protocols communicate how many of the objects are there to expect. You have, in a DNS frame, for instance, you have a count value in the header. You know, you need to pass like 3 requests. Or you can have something like on the IP options, that you have a special type value for this is the end of the list. So you try parsing your byte vector until you hit a certain field value. Or it also happens that you need to compute the start offset of the next field, and now you have to stop parsing when you reach the end of the field, which is also the case for IP options. It's perfectly legal to have IP options which don't end with an end of IP options, but which end by being right next to the start of the payload. So it was a little bit tricky to get the parsing algorithms correct in all cases like that.
Yeah, that's a field class hierarchy. So we have a field. A field is an element of a container frame. So we have two different types of fields. We have variably typed fields, that's payload in an Ethernet frame or payload in an IPv4 frame. Then we have statically typed fields. Yeah, there are difference between single fields and repeated fields in statically typed fields. So we have a single field like the source address or the destination address in an Ethernet frame. A repeated field would be the IP options. So we have self-delimited repeated fields like IP options, which is also externally delimited. And we have also comb-repeated fields like the name server field in the DNS frame, like already told. Yeah, that's a code example for our syntax. So it's an Ethernet frame. So that's the way we specify how an Ethernet frame looks in our domain-specific language. So we start with a field destination address of type MAC address. Yeah. Then next is a source address of type MAC address. Then there is a type code. Type code is a 2-byte big endian unsigned integer. Then we have a variably typed field payload, which depends on the on what the value of the type code is, which type the payload is. Yeah, and I think that's it.
Yeah. I know if you look at that for the very first time, we're already very used to it, and look at it and say it doesn't need any explanation. Of course, the contrary is the case. Do you have the feeling you roughly understand what this is trying to say, what it's trying to communicate? Who doesn't understand it? What's going on? That's not so many people, that's good. What happens below the hood here is that we use the Dylan macro facility for basically coming up with our own description. So what you see here looks a little bit like a class definition would look like it. But the Dylan macro system is pretty unique in that it does pattern matching on the abstract syntax tree. One could say that you can add new rules to the grammar from your user code, and that's what we do here. So defined protocol doesn't exist at all. We wrote it, and but some of the stuff we write there, like the type function colon, that's actually a Dylan expression. So we are able to reuse Dylan expressions in our description languages at places where we need it, where we need the dynamic features. Then MAC address is a leaf frame, which we already saw. 2-byte big endian unsigned integer is also a leaf frame. Those are pretty fine, and they're pretty boring to look at. It's like 3 lines defining the generic case of translating big endian integers. Then another line that says, oh, make me 102 bytes in size, so we won't go do that. There's one more interesting aspect here, and that's that in the first line that says define protocol Ethernet frame, it says open bracket header frame, close bracket. And that's an inheritance feature. Header frames are our definition for the typical case that you have a header and a payload. And this occurs so often that we just abstracted it away. So there is a field payload, which we define here, and a header frame requires you to have a payload. And if you use header frame, it has some effects on how stuff is displayed, etc. And how layering works at a later stage. Okay.
Yeah, now to our parsing algorithm. So to parse a payload of a Ethernet frame, it's quite easy. So you first have to look what the value of the type code is. Well, it's in this byte vector, it would be 0x800. So if a user accesses the payload of an Ethernet frame in our framework, and you have a byte vector as input, it first accesses the bytes 12 to 14 for the type code, and then looks up what the type of the payload should be, and then parses the payload or generates a class of that type. Okay, to parse the payload, so Ethernet frame was quite easy because it's everything is static, so the payload is at a static offset and so on. Parsing an IPv4 payload is a bit more difficult, so the payload depends on the protocol fields. So the protocol fields tells us what type the payload should be. So to parse a payload of an IPv4 frame, we first have to access the protocol. So once we have it, like one is ICMP, we have to look up where the payload starts and where it ends. So we have to access the header length and the length field in the IPv4 field. So parsing the header length equals to 5 and the length to 100, then we come up with an ICMP frame which starts at 20 and ends at 100 at the byte vector. So we just generate an ICMP frame and give it a byte vector which size is 80 and starts at 20 of the original byte vector.
And just to make it clear, if you write such a protocol definition, you don't need to write the parser that does that. There's a generic parser which looks at the structure you define and automatically does the right parsing for you. So it will look for the first field with the static offset and work its way from there to keep the times, etc.
Yeah, that's the definition of an IPv4 frame.
It's probably a little bit hard to read, but it basically puts together some fragments we've seen on previous slides. You have version in the beginning with the default value of 4, then in the next line a header length, which again is a 4-bit unsigned integer, and the fixer function to compute it while assembling. Yeah, you all know those fields. The header checksum again is an interesting case because it requires access to the actual byte vector to compute. So you cannot use a regular fixer function where you say, give me the value of the field. You need to hand the almost completely built package to some function that will compute the value for you. For that, we provide an extra hook, an extra global fix-up, which is called when assembling the frame. Yeah, what you also see here, what we haven't seen yet, is the options field, which is a repeated field. And it has here a callback for reached end, where you write code that returns true when you hold in your hands the last element of the actor. So in that case, if the value we see is an instance of an end of option, IP option, here we should be able to stop parsing the IP options. Okay, so the next step is showing what you can actually do with that after so much theory. And here's an example of how you actually use the API. So assume that we have defined your IPv4 packet frame format. Then the next step you can say is you have a generic function parse frame where you pass the type of the frame you want to parse and the packet where it comes from, obviously. And you get back a high-level object where you can use a slot access notation, like you could access what C++ calls the members of a class, and every language calls it differently, but it just looks like a regular class access. So from the field source address, there is a getter function generated, which is also called source address. You can just print out the source address, and we'll know that the source address is an IPv4 address, and there will be a print method defined for IPv4 address with a leaf frame, and it will work.
Okay, that was parsing. Parsing of Ethernet frames or parsing of protocols is done by our framework by simply describing the protocol definition. But the same is true for assembling. You don't have to write a line of code to do it, to assemble a frame in our framework. So, simply by defining the protocol enables you to access assembly frame, which is also a method. And assembly is quite difficult because you have at least 4 sources of data where it can come from or where it must come from. It's user provided, that's fields in an IPv4 packet like source address and destination address. Protocol is not quite true here. It's not user provided. It has default values if you provide a payload. Then you have default values, so protocol default values, which are specified in any ROC or something, like version, type of service, identification. Yeah, identification is simply random generator, then flags, fragmentation offset, TTL, and so on. Then you have some fields which have fixer functions like header length and length. And then at the last you have another fixer function which needs to be computed at the end. So when assembly is almost done, like the checksum field of an IPv4 frame, which is the 16-bit checksum, so the 16-bit sum of the whole header. Yeah, so we came up that all the fields can be user provided. So if you want to have an IPv4 frame, which version field has 23 or which has 50, you can simply write it. You can say, make an IPv4 frame which version field is 50.
Yeah, the point is that for obvious reasons we wanted to be able to create broken packets too. Okay, so we've seen here that of the many fields in IPv4 frame, there are only some that actually need to be provided by the user. The code for that looks like that. You create an IPv4 frame and then you pass keyword value pairs. Again, the name of the field, then the colon, and the constructor for the appropriate class. So the source address needs to be an IPv4 address. So there's a constructor that creates an IPv4 address from a printed representation for us. Or maybe you have a different source of an IPv4 address, but you're also always handing around high-level packets. And as you see, you specify source address, destination address, and your protocol. And then you can get at the byte vector by basically calling the assemble frame function, which gives you an intermediate result, which is again an assembled byte vector, but it keeps some high-level information in case you later want to modify the packet. Because if you write a port scan or something, you don't want to create the whole packet all the time, but you also want to change some fields and basically do in-place assembly. That's why you need that extra dot packet to get at the packet. But it's also, again, very simple to use. Once you have defined your IPv4, you can easily create packets. Yeah, that's an example because we haven't seen it yet. It's actually part of the definition. This is how our header checksum computation works like. We get in the IPv4 frame, then have a function calculate checksum, which we omitted here, which does the actual computation if given the packet, and then sets the header checksum field. The colon equals is an assignment, obviously. it assigns that value to the result of the computation. And you see here that not only are getters generated for every field in the frame, but there are also setters generated. And yeah, one step back, we have actually two representations for packets under node. One is a purely high-level representation, which remembers for every field the high-level value. The other one is a representation that associates a byte vector with the cache of values already computed. And so the setter functions do two different things, depending on what you have. It will either change your packet right away, if you have a packet, or it will change the high-level representation. So you can also modify packets. That's what's done here. And then recursively, the fixer for the payload of the frame is called Andreas.
Okay, that was parsing and assembly of protocol definition. That was the first subproblem we encountered and solved. Well, I think we solved a more generic problem than protocol definitions, because we solved the problem of parsing and assembly of any binary data stream which is byte-oriented. So you can also write a linker with our definition, so you can write a protocol definition from elf header or from elf file and provide some code to implement the actual linker.
Yeah. Or you could write an analysis tool for file systems. The nice thing, since we have a complete description of the framework and an abstract parser for it, we can determine if there are any gaps, if there are unexplained bytes in some packets. So we have definition at an instance of that definition. We can basically write a generic information hiding detection tool on top of it by just outputting all unexplained bytes. You could also write parsers for your image files, etc., in language. But we weren't done with the network stuff yet, and so we talk about that a little more. The next obvious feature you want to have is filters for your network packets. And since we already know the names of the fields and the types of the fields, it was pretty easy to come up with a language that looks like the Ethereal, a little bit like the Ethereal filter language. So you say type.filtName equals some value, and it will generate a filter expression that selects those types of packets for you. And you can compose those expressions using AND, OR, and NOT rules. And you can also check for presence of frames. I think it should be pretty obvious. It was a 150-line set.
Yeah. Okay. The next thing we came up with was flow graph, the flow framework. So we have modules like a filter which has one input and one output, or a demultiplexer. Demultiplexer has one input and multiple outputs, and each output is associated with a filter rule. So if you have a demultiplexer, you can insert a filter rule and you get an output. So you get an output where the package which matches the filter rule will come out.
As a basic flow graph, the idea is that you push your packets along the edges, and the nodes in your graph do the processing. So you have some node which emits packets from the Ethernet interface, and you could then put that into a filter and then put that in a decapsulator that removes the first header, and or the demultiplexer which associates a number of outputs with the rule in each. So you can then connect one to a printing module and the other one to diff null or whatever.
Yeah, then obviously also fan-in, where you have multiple inputs and one output, and the closure node where you have one input and no output, but you have a closure, so a function which only receives the packets and do some processing, adding to a global list or whatever. Yeah, an example, or let's start to read. An example would be a simple sniffer where you simply make an Ethernet frame. So that's Ethernet interface. So that's actual 3 lines of code to have a simple sniffer.
That's what the implementation of TCP looks like in our framework. It's 3 lines. You create the Ethernet interface. You create a summary printer node that the Ethernet interface will capture the packets and emit it to you on one side. It will also accept packets on the other side. So this is left unconnected here. Then in the second line, a summary printer is created, which prints a summary of all packets. That's also part of our definition language, that you can say summary, colon, then the format string, and the number of parameters to get a nice printing. And then that summary printer is connected to the Ethernet interface, and in the third line, the top-level entry function is called, and it will start printing the packets.
Yeah, a bit more complex is simple sniffer with the filter, where you simply generate the filter. In this case, we filter out all ARP frames. So we connect the Ethernet interface to the filter and the filter to the summary printer. Yeah. Another example would be a bridge, where you have two Ethernet interfaces and you connect the output of one of them to the other and the output of the other to the one. And then call top level on each interface to provide a bridge which simply bridges all packets from one interface to another and the other way around.
Okay, so this graph, this flow graph solves a number of problems for us, but it doesn't solve a very important problem, and that's the one of layers stacking. You want to be able to say, oh, I want to speak TCP over IP over Ethernet. Or you want to say, I want to speak TCP over IP over ICMP over PPP over Ethernet. Or something. So to just plug layers into each other. And we found that we need another abstraction here, which internally consists of a number of flow graph nodes. Like we have an Ethernet layer here, which it's a little bit simple, because in reality you have queues and that queue control a complete system, but that's something that's abstracted away here. So it consists of our source and sink of packets, which is the Ethernet interface. Then we have a demultiplexer to provide higher layers with their appropriate packets. And we have a fan-in, which is where the higher layers return their packets to. And of course, if you want to register as a protocol implementation one layer above that, you have to have one demultiplexer output and one fan-in input, and be connected together in a structure we call a socket, surprisingly. And that's a little bit more involved again, because what we do here is basically on the way up, stripping the appropriate layer header, and on the way down, we edit again. And that we do by providing so when you create a socket, you say, hey pal, I'm gonna speak Ethernet type code 800. Please pass me everything for that. And it will then create the appropriate filter to give you type code 800. And it will also create a template frame which sets type code to 800 when somebody passes in input from the top. So to the top, the decapsulator strips the header. There comes an Ethernet frame from the demultiplexer, and is decapsulated. Only the payload is passed up to the actual implementation on top of that. The other way down is the opposite. It adds a header to the beginning by using the template frame, and that's what we call a completer. And the information needed. So the instance we have here is R, where we have an ARP handler, which is the layer sitting on top of that, using a socket to communicate with the layer below. And where the ARP handler has an ARP table, obviously it knows an ARP address that to respond to, etc., etc. And it fills the filter rules in the template frames with some values like type code 806 and the source address of our ARP of our host. The implementation of the IP layer is a little more complex. One thing is that for TCP IP, OSI abstraction doesn't work too well. You have some mixing of layers. So, for instance, it's always interesting to ask who's speaking ARP. Is it layer 2 or layer 3 issue? And the reality is that you have some part of your IP layer which doesn't know anything about the physical layer below it. And then we have what we call adapters, that actually know the pesky details of the protocol below. So, for instance, we have an IP over Ethernet adapter, and we have an IP over serial line adapter, for instance. And the IP over Ethernet adapter knows that you have to talk ARP on the wire to be able to address hosts. So the IP over Ethernet adapter talks to an ARP handler, which uses an ARP socket to connect to the Ethernet layer, and it also talks to the IP layer to be able to send packets, because you have to do an ARP lookup before you can pass it on to the Ethernet layer. Okay, so much for our overview. We already have implemented a number of protocols, more or less. There's only so much time we have. We have written some network services. We have TCP, I would say almost running. We have to work on retransmission, timing issues, stuff like that, but the framework for that is there. And applications we imagine are stuff like firewalls, IDS systems, network analysis tools. And as a tool that's very, very bitterly needed, we started writing a replacement for Wireshark, which we call Network Night Vision. And we have released it on networknightvision.com. It's an 0.0.1 version, so don't expect it to do anything remotely useful. But it would be nice if you look at it and say, the top 3 features I'm missing are, and send it to us, so we get an idea of what people need. Because I think we are quite sure that despite a lot of bugs which are in the software, none of those bugs is exploitable, because we designed the software in a way that actively defends against this type of attack in stuff of the system, in the architecture of the system.
Okay, to the conclusion, we came to the conclusion that software architecture is software security. So to have a well-designed software architecture, you get software security. So you have language features which provide security. Yeah, we provide the IP stack without remote exploits. Complete IP stack without remote exploits. To make a few announcements, we have on the one hand networknightvision.com, where we have our installer placed. Then we have the Drone Hackers Conference Europe 2006 right at this congress down in the Hype Center. Today there's in the workshop room from 15:30 to 17 Dome introduction workshop, and tomorrow in the workshop room there's from 21:30 to 23:30 there's a packetizer workshop where I will show some how to implement a real protocol. So come around and look at it. I will implement IPv6 if no one else comes up with a better idea what protocol to implement.
Okay. So finally, I think if somebody has questions, we can already pass around the microphone. And meanwhile, I'm trying to make Riverberg to give you a demonstration of Network Night Vision.
Wasn't the protocol file in an IP4 packet a 4-bit value? So how could you pass 23 in it without an overflow?
Yeah, that wouldn't work. I remember that and came to the example that 15 would be adequate. So we have a high-level representation of the protocol field as 4 bits. So we have a limited integer. You can only fill in from 0 to 15.
Hello? How do you handle when you have too many packets, like 1 GB per second being dropped on your line? How does it perform? Do you have a large frame drop, or do you do something about that?
Well, we have the lazy parsing algorithm and the lazy assembly algorithm. So we generate high-level objects on demand, so only when we really need them. So it's quite lazy. We are quite sure that it performs well. We haven't yet do any performance optimizations, but we have tried another appliance, which is a transparent bridge, which performs quite well at about 100 Mbit. So we are quite sure that once we are ready with the proof of concept stuff, we will go to the optimization stage. And due to the features of Dome we have, that we can provide types and get more optimizations in Dome better.
Okay. Yeah, this is network night vision. It probably looks familiar to you. We have the list view of packets up here. Then there's a tree view of packets. Let's see whether we find something more interesting than an upframe. Like we have a DHCP message here. And yeah, you can scroll down. You have a hex highlight down there. As you would expected. Then on top here, you can enter the filter expressions we talked about. And we have upframes here. And yeah, one thing that Ethereal or Wireshark can't do yet, what we can do, is say re-inject packet. And then look at what happens. Nothing much is unreachable, obviously. Okay, or no TCP traffic. That's too bad, so I can't show you the TCP kill feature. Yeah, I could click a website, that's correct. There we have TCP traffic. And you see here the reset, and the answer to the reset connection is done. Yeah, so that's also the direction we want to go into. It's not just a passive analysis tool, but we would like to extend it into an active analysis tool. So maybe Scapy with the user interface would be another good subtitle. And maybe even extend it to use some knowledge-based representation for making inferences of the packets you see, etc.
What you show us is how to specify how packages are assembled and so on. But how can you specify how the packets of a protocol relate to each other? So one packet has to follow a second and so on. Is it possible to filter for it? So only packets which were first demanded from a specified host or something.
I'm not sure what you mean. If you mean analysis of state between packets, that's something we don't do at that level. So packet always cares about itself. The relationship between packets is something you want to express at a higher level using a knowledge representation system, where you have first order predicate rules that specify relationships between packets and the events that are triggered. And we plan to use open, the power loop is called the power loop inference engine to actually do analysis on top of that. But we don't have that yet. Okay, I think 2 more questions and then we run out of time.
Hi. Can you compare to more different dumps? Because one of the problems I have with Ethereal is that I can't compare to different dumps, big dumps, in terms of like, for example, I was trying to have 2 dumps of 2 different testbeds, and I was trying to compute and see if one testbed was sending different packets in different orders or stuff like that, which pretty much means doing a diff, but not just like text if you have to look at sequence numbers and stuff like that.
Well, it's obviously not something we have finished yet, but I think it's doable in our framework. It's a reasonable amount of code to write something like that, and it's a good idea.
Even more than 2 dumps at the same time.
Yeah.
Hello. I was wondering, you mentioned you wanted to do responsible
generic stack. So you could do like IP on top of Ethernet, on top of TCP or whatever. Okay, I noticed you solved the problem of, for example, IP communicating with Ethernet alone by using adapters. So your IT module has a built-in adapter that has knowledge of the inner details of the Bogk protocol. Now I'm wondering how you solve the generic case though. Because, okay, that module works if it has Ethernet below it, or maybe a few more if you need a few adapters. But do you have a solution for the generic case? Where I want to put IP on top of some arbitrary protocol?
If you want to talk, say, IP over ICP, you have to have some place where you specify that you actually want to create an ICP packet now. And that happens in an adapter. So the answer is you have to write an adapter, but that's probably 5 lines of code.
You can't create, the user can't create an adapter and plug it into the...
Yeah. Okay. So I think we run out of time for questions. We thank you very much for being here and listening to our talk.